So this is a 2.7 meter diameter cast iron tunnel, and almost 2 meters beneath my feet there is a gigantic 11 meter diameter Crossrail tunnel that is being excavated right now to form one of Crossrail's platform tunnel stations.
The Crossrail project is the largest civil engineering project presently under construction in the whole of Europe. So it's a very large underground construction project with all sorts of engineering challenges. One of the most important ones being, how is it possible to construct large tunnels underneath urban infrastructure without causing any distress to those buildings and other tunnels. And at Liverpool Street Station, there is one example of a very intricate part of the engineering of Crossrail, which involves constructing some very large new tunnels directly underneath other tunnels, including the old post office railway tunnel.
Well, this is an exceptional event in the tunneling history because you have the Crossrail platform that is being excavated right under us, and it runs for 100 meters parallel to this tunnel. This has never happened before. A lot of movements are going to be transferred from that excavation to our tunnel, and that makes this project of two particular importance. One is because we get the chance to study the cast iron behavior in detail that have not been done before. And secondly, we get to trial some of our groundbreaking technologies.
So the cast iron tunnel is formed of individual segments, which are constructed into a ring of segments. This is commonly known as the segment panel, or the pan, and these are the flanges. In this case, these are the circumferential flanges, and these are the radial flanges. Particularly at this point along the crown of the tunnel, we can detect whether the tunnel is deforming in a uniform bending, i.e. tube-type mode, or in more of a shearing mode, where the individual rings all displace in kind of a vertical shear, like a saw tooth.
In essence, the main problem is how much will the post office railway tunnel move, and will that movement be a tolerably small amount, and can we be sure of that, and exactly what kind of mechanics are involved in the way in which it moves, all of which is quite complex. And so we have a variety of different sensors. We have optical fibre to measure the strain longitudinally all the way along the post office railway tunnel, which really, the optical fibre can show us how the post office railway tunnel deforms, how it bends, if you like. We also have displacement transducers, which are installed in a whole lot of locations along the post office railway tunnel without any wires. So they are actually able to measure displacements of one part of the post office railway tunnel relative to the next part, and then wirelessly transmit the data to a receiving station. And thirdly, we're using some very exciting new computer vision techniques that we've developed here at Cambridge. So we have these three new technologies, all of which are all quite well tried, quite well proven, but need to be applied in real live situations such as the post office railway tunnel.
The sensors itself, they are very small and light and very long battery life. So we are approaching nearly zero power, which is what we're trying to achieve for long term. And the sensors, they measure in this tunnel, in particularly humidity, temperature, acceleration, and tilt. That will enable us to tell the deformation basically in the tunnel.
By installing the kind of sensors that CSIC is working with, that can actually then give a continuous update as to how much those tunnels might be deforming, what changes are taking place. And by putting these kinds of sensors into that kind of infrastructure, we can really answer a lot of important questions about the value of our current infrastructure, the future of it, whether it needs to be maintained, whether it needs to be replaced. All those kind of questions can be much better quantified.